Greetings, everyone. I want to continue with chapter 8. I need to do the exercise, the problem, some of the problems in the exercise set for chapter 8. I'm actually going to have to do it in two parts because I haven't finished all the exercises that I want to do in chapter 8 yet. So there'll be a part 1, which will be this video. There'll be a part 2 for the chapter 8 exercise set, and then in addition to that, there's an appendix which I need to get through, and then an exercise set for the appendix. So we still got a little ways to go in chapter 8 in the Spivak book, but we're moving ahead. So uh, let's go ahead and just work on where to put this. Uh, let's work on the exercises that I've done so far in chapter 8. So here are the problems. We'll start with question number 5. Right, so question 5 says, so there's a few parts to it. Part A says, suppose that y minus x is greater than 1. Prove that there is an integer k such that x less than k less than y. He gives a hint here, and actually he gives hints for a lot of the problems in this exercise set. Because the problems are kind of important. There's a lot, that's which is why I want to do a lot of them, because some of the problems introduce new concepts and definitions. So I want to make sure that I at least get through all of those important ones. This problem is important because it introduces the fact that the rationals and the irrationals are a dense set. But anyway, here's the hint for part A. Let L be the largest integer satisfying L less than equal to X, and consider L plus 1. That's the hint. So let's actually do that. So let L be defined as in the hint, then L obviously is less than or equal to X, which implies that X is less than or equal to L plus 1, right? Because, well, first of all, if X is an integer, then L equals X. However, if X is not an integer, then L will be a distance less than 1 away from X. So L plus 1 will have to be greater than X. And from that inequality, L less than or equal to X, we get that L plus 1 is less than or equal to X plus 1 by just adding 1 to both sides of the inequality. And obviously X plus 1 is less than Y because of the assumption that Y minus X is, by the assumption that y minus x is greater than 1. Okay, and that's the proof basically for that part. Right, going on to part B. Suppose x is less than y. Prove that there is a rational number r such that x less than r less than y. Again, here he gives a hint. He says if 1 over n is less than y minus x, then ny minus nx is greater than 1. And he also asks a question in the textbook for this part too. He says, why have parts A and B been postponed until this problem set? I can answer that question first before we look at the proof. It's because we haven't established the Archimedean property of the real numbers before this section, so that's why. But let's go ahead and do the proof. I use his hint here. So let x less than y. Then there is a natural number n such that 1 over n is less than y minus x by theorem 8.3, which is the Archimedean principle for the real numbers. So 1 is less than ny minus nx, just from algebra, right? You just multiply the inequality through by n, and that gives you that equivalent form. And by part A, there's an integer k such that nx is less than k less than ny, which implies that x is less than k over n less than y by just dividing by n. Okay, so we used part A to do this, and the Archimedean principle. All right, so then r equals k over n is such a rational number. So that shows that between any two real numbers, there is a rational number, which he hasn't defined density of a set yet, but he'll do that in the next question. So, but what this shows is that the rational numbers are dense in the real numbers. Right, so going on to part C. Suppose that r is less than s are rational numbers. Prove that there is an irrational number between r and s. Again, he gives a hint here. He says, as a start, you know that there is an irrational number between 0 and 1. So let's go ahead and use that hint. Right, here's my proof. Pick n in the natural numbers large enough so that 1 over n is less than s minus r. We could do that by the Archimedean principle. Then 1 over radical 2n is less than 1 over n, because radical 2 is a number between sorry, is a number bigger than 1. So, and that means that 1 over radical 2 is less than 1. Um, that's less than 1 over n, which is less than s minus r by uh, our assumption here. We chose n to be large enough to make that happen. Okay, that implies that 1 is less than root 2 ns minus root 2 nr, which implies there's a natural number there's a natural number k such that radical 2 nr less than k less than, did I read that part already? Anyway, there's a natural number k such that root 2 nr less than k less than root 2 ns. That implies that r is less than k over root 2 n less than s, and that's your irrational number. The product of an irrational number and a rational number is always irrational. I don't remember if we might have proved that in a previous section, but actually it's been so long since I've done some of the chapters here. I forget if we actually proved that in this book, but it's easily proven with a proof by contradiction. So that k over radical 2n is an irrational number between r and s. Therefore, that's an irrational number between r and s, which is what they wanted us to show. So not only are the rationals dense in the real numbers, but the irrationals are also dense in the real numbers. Right? Part D says, suppose x less than y, prove that there's an irrational number between x and y. It just follows from all the part A through C that we just showed. So there's really nothing to show there. It just follows directly from the properties here. Because if you have any two real numbers, x and y, you can find two irrational numbers strictly, between x and y, and between those you can find an irrational number. But it just follows from the parts of the problem. Okay, going on to question 6. So here he defines what it means for a set to be dense in another set. So a set A of real numbers is said to be dense if every open interval contains a point of A. For example, problem 5, which is the one we just did, shows that the set of rational numbers and the set of irrational numbers are each dense. Okay, and there's a bunch of parts of this question as well. So part A says, prove that if f is continuous and f of x equals 0 for all numbers x in a dense set A, then f of x is equal to 0 for all x. All right, so here's the proof. Assume for the sake of contradiction that there's an x, a real number x, such that f of x is not 0. Then without loss of generality, we can assume that f of x is positive. If it's negative, then we can just consider the function negative f, and so that's why we can do it without loss of generality. Then there is a delta greater than 0, such that f of y greater than 0 for all y in the open interval from x minus delta to x plus delta. This contradicts that f is 0 on a dense set A, and that's it. All right, part B, prove that if f and g are continuous and f of x equals g of x for all x in a dense set A, then f of x equals g of x for all x. Again, here's our proof. It's pretty straightforward. This follows from part A, since h equals f minus g is a continuous function with h of x equals 0 on a dense set A. So it's just that simple. Part C, if we assume that f of x is greater than or equal to g of x for all x in A, show that f of x is greater than g of x for all x. And then he asks the question, can greater than or equal be replaced by greater than throughout? Let's answer the question first, which I have written down here, and then we'll look at the proof. So the answer to the second question is no. For example, if you take these two functions, f of x equals absolute value x and g of x equals 1/2 absolute value x, if you graph them, they look like, I'll have to do them in different colors just so you can distinguish between them. So one of them looks like that, one of them looks like this. So obviously the red graph is less than or equal to the blue graph on a dense set of R, dense subset of R. But notice that it's not strictly the blue graph is not strictly greater than g of x for all x. For example, at the origin, it's not. All right, so let's actually prove the proposition now. Okay, so assume for the sake of contradiction that f of x is less than g of x for some x, some real number x, then 0 less than g of x minus f of x equals g minus f of x. Then there's a delta greater than 0 such that g minus f of y is greater than 0 for all y in the open interval from x minus delta to x plus delta, which contradicts that g minus f of x is less than or equal to 0 on a dense set A. And there you go. Okay. Going on to question 7, prove that if f is continuous and f of x plus y equals f of x plus f of y for all x and y, then there's a number c such that f of x equals cx for all x. This conclusion can be demonstrated simply by combining the results of two problems. That's Spivak's note. So the two problems he's referring to is there's a problem in chapter 3 that we did, which is actually in the exercise set for chapter 3 video that I made. So if you want to see that, you can go back to the exercise set solutions, the video where I do that on the channel, and you can see that one. I say which problem it is in the proof, so I'll point that out when we get to it. And also there's from the previous problem that we just did, there's also something that we need for that. So he also has here in the problem what he calls a point of information. He says there do exist non-continuous functions f satisfying f of x plus y equals f of x plus f of y for all x and y, but we cannot prove this now. In fact, this simple question involves ideas that are usually never mentioned in undergraduate courses, and he refers the reader to the book Theory of Sets by E. Kamke. And maybe I'll mention this book further in my vlog for the March, my March, beginning of March vlog, because this book has been referred to by in several things that I was reading in February. So I don't actually own this book, but I might have to look into seeing if I can get a copy because, like I said, it's been referred to a bunch of times in stuff that I've been doing over the last month. So it might be worth taking a look at. But anyway, let's get to the proof of this problem. Okay, so the proof says we know f of r equals f of 1 times r for any rational number r by problem 316. That's the problem that in chapter 3 that I was referring to before. So if you go to the chapter 3 exercise video on the channel, that's one of the problems that I go over, so you can see the solution to the problem, and you can see the solution to it there. But anyway, we're using the result of that exercise. Also, f of x equals f of 1 times x on a dense set of R. Therefore, by problem 8.6, which is the one that we did right before this, above, f of x equals cx for all x and c equals f of 1. And that's the proof. It just follows from those two propositions that we proved from previous examples. Okay, question 8. Suppose that f is a function such that f of a, sorry, just gonna adjust myself here. Suppose that f is a function such that f of a is less than or equal to f of b whenever a is less than b. He refers to you to a picture, figure 6 that's in the book. Let me just show it to you real quick. This is figure 6. Hopefully that shows up on the video. So this is the figure that he's referring to. And then there's a couple parts. So part A says prove that the left-hand limit of f of x as x approaches a and the right-hand limit of f of x as x approaches a both exist. And he gives a hint. Why is this problem in this chapter? I'll answer that question. I don't remember if I actually wrote the solution to that question here, so I'll just say it. It's because in order to do this, you need the least upper bound property, and that's what chapter 8 was on. So okay, so here's my proof. Let a be a real number. Then for any x less than a, f of x, excuse me, f of x less than equal f of a. Therefore, the set f of x where such that x is less than a is bounded above by f of a plus 1, which means that s equals the supremum of f of x less than a. in R, so meaning that the supremum exists, right, by the least upper bound property. Assume for the sake of contradiction that for some epsilon greater than 0 and all delta greater than 0, there's an x in the open interval from a minus delta to a, for which absolute value f of x minus s greater than equal to epsilon implies f of x minus s greater than or equal to epsilon, or f of x minus s less than or equal to negative epsilon, which implies f of x greater than or equal to s plus epsilon, or f of x less than or equal to s minus epsilon. Both of these situations contradict that s is the supremum of that set. Therefore, the limit, the left-hand limit has to exist, and it's equal to s. And a similar argument shows that the right-hand limit exists and it's equal to the infimum of this set. It's the infimum of the set f of x such that x is greater than a. I skipped that proof because it's virtually identical to the one that we just did, just, with some things switched around. But it's a similar, similar proof. Here's part B. Prove that f never has a removable discontinuity, and he remarks that this terminology comes from problem 617. Again, 617 is a problem that we did in the video for chapter 6, so you can take a look at that if you want to. Here's the proof. Let f be discontinuous at a point A in R. Assume for the sake of contradiction that the limit of f of x as x approaches A exists and is not equal to f of A. If L equals the limit as x approaches A, then L is the supremum of f of x, such that x is less than or equal to a, which should be also equal to the infimum of f of x as x approaches a, because we're assuming the limit exists, and from part A that should follow, and we're assuming that that's not f of a. However, this implies that f of a is greater than or equal to L and less than or equal to L by the fact that f of x is less than or equal to f of y for all x less than y, and by definition of the supremum and the infimum. Again, that follows from the previous part. This contradicts that f is discontinuous at x equals a, therefore no such removable discontinuity exists for f. And that's it. Okay, this is a third part here. Prove that if f satisfies the conclusion of the intermediate value theorem, then f is continuous. So let's do that here. Here's the proof. Let a less than b and f of a less than or equal to n less than or equal to f of b, and that for any such n, there's a c with a less than c less than b, such that f of c is equal to n. So this isn't the intermediate value theorem in complete generality, but you could do the other, the other case as well, and it'll work just the same. By other case, I mean like this, right? So the general intermediate value theorem just says that for any n between f of a and f of b. Okay, so then limit as x goes to c of f of x is equal to n equals f of c by the argument in part A and B. Therefore, f is continuous on R since A and B were chosen arbitrarily. In other words, there's no reason that there's nothing special about A and B. You can do this for any two real numbers. Okay, so that's what number? Whoops, what number was that? Question number. Question 8. Okay, next what I did was question 10. Suppose alpha is greater than 0. Prove that every number x can be written uniquely in the form x equals k alpha plus x prime, where k is an integer and 0 less than equal to x prime less than alpha. So let's go ahead and do that. Let x alpha be real numbers with alpha greater than 0, and choose k to be the floor of x over alpha, meaning it's the greatest integer less than or equal to x over alpha. Then k alpha is less than or equal to x, and we can take x prime to be the distance between x and k alpha. Then x prime is greater than or equal to 0 and less than alpha, since x prime equals x minus k alpha greater than equal to alpha. That implies that x is greater than or equal to k plus 1 alpha, contradicting that k is the floor of x over alpha. Furthermore, x equals x prime plus k alpha. By just adding, you can just add k alpha to both sides here. Over here, I'm talking about. Just add k alpha to both sides. Okay, 11, question 11, part A says, suppose that A1, A2, A3, dot, 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 is a sequence of positive numbers with AN plus 1 less than equal AN over 2. Prove that for any epsilon greater than 0, there's some n with AN less than epsilon. In order to do that, I started by proving a lemma, which is this statement here, AN plus 1 less than or equal to A1 over 2 to the n for all n in n. I did this by induction, so the base step is A2 less than or equal to A1 over 2. That follows directly from the recursive definition that we have written over here. And then going on to the inductive step, assume AN plus 1 is less than or equal to A1 over 2 to the n for some n in n, and then consider AN plus 2. That's less than or equal to AN plus 1 over 2, again, by the recursive definition. And by the lemma, that's less than or equal to A1 over 2 to the n plus 1 by the inductive hypothesis. Okay, so using that lemma, let epsilon greater than 0, choose n in the natural numbers large enough so that A1 is less than 2 to the n minus 1 epsilon, then AN is less than or equal to A1 over 2 to the n minus 1, which is less than epsilon. Okay, here's part B. Suppose P is a regular polygon inscribed inside a circle. If P prime is the inscribed regular polygon with twice as many sides, show that the difference between the area of the circle and the area of P prime is less than half the difference between the area of the circle and the area of P. He says use figure 7, which is this figure from the book. I actually have it redrawn down below, but just to show you the actual picture in the book, this is figure 7. Right, so what he wants us to show is that, so this distance here, right, that distance there is less than, let's see, I have to do a different color here, is less than half of this distance here. All right. Sorry, is less than half of the whole distance. So less than the red area plus the brown area here. So going back here, so you can see actually I redrew the figure 7 over here. So if B is the blue area, R is the red area, and G is the green area, then from the picture you can see that B is R plus G, right? The blue area is the red area plus the green area, which implies that the red area is the blue area minus the green area, which is less than the blue area, obviously, from just, because we're subtracting G from it here. If you multiply the inequality over here by 1/2, you get 1/2 R less than 1/2 B. 1/2 R is the same thing as R minus 1/2 R, which is less than 1/2 B. And then you just add 1/2 R to both sides. That shows that R is less than 1/2 B plus 1/2 R, which is the same thing as half of B plus R, the blue area plus the red area. So that shows that the red area is less than half of the, the circular area over there, or the area of that circular sector. I don't know what to call it. It's that part of the the area, that part of the circle. Sorry, it's really hot in this room and it's making it hard to think straight. Okay. Okay, so that shows that like I said, area of the circle minus the area of the 2 n-gon, that's the red area here, is less than 1/2 of the area of the circle minus the area of the n-gon. You could think about, like, just take, I didn't draw the entire n-gon here, but this property holds for all, for a regular n-gon here. So I didn't really, you get the picture. It's not easy to draw here, which is why I didn't attempt it. But okay, part C, prove that there's a regular polygon P inscribed in a circle with area as close as desired to the area of the circle. In order to do part C, you will need part A. This was clear to the Greeks, who used part A as the basis for their entire treatment of proportion and area. Speaking of which, when we get around to it, there's a couple books that I have over here. Just let me stop the screen share for 1 second. When we get to that's the topic in Stilwell's book, Mathematics and Its History. He has a full treatment of that, so we'll look at that in depth at some point. Also, I don't think I've talked about this book on the channel, but he talks about that in this book as well. This is The Calculus, a Genetic Approach by Otto Toeplitz. This book has a foreword by David Brassoud, by the way. It's a good read. I just started reading through this, and it's really interesting. Genetic approach means that it's the calculus is developed from in the normal way that or the natural way, maybe I should say, that calculus developed through history, which is interesting. So you guys know my interest in mathematical history, so okay. Just going back to where we left off over here. By calculating the areas of polygons, this method, which is called the method of exhaustion, allows computations of pi to any decimal accuracy. Archimedes used it to show that 223/71 less than pi less than 22/7. This is an approximation that they they show you usually in like grade school or so on. That's what you use as your approximation, but it has far greater theoretical importance. Right, let's go ahead and do the proof. Okay, so let Pn be a regular n-gon inscribed inside a circle, which I'm calling theta. Define An to be the area of theta minus the area of the regular n-gon P, where I'm just describing that here. So A of Pn and A of theta are the areas of the regular n-gon and the circle respectively. Then An plus 1 less than An/2 by part B. That's what we just proved in the previous part. Then for any epsilon greater than 0, there's an n in n such that an is less than epsilon by part A. What that means is that, we can approximate the area of the circle to any degree of accuracy by taking an inscribed regular n-gon with enough sides. So, just make the sides big enough, the number of sides big enough, and you can get within any degree of accuracy that you want. Okay, part D, using the fact that the areas of two regular polygons with the same number of sides have the same ratio as the square of their sides, prove that the areas of two circles have the same ratio as the square of their radii. And he gives a hint here. Deduce a contradiction from the assumption that the ratio of the areas is greater or less than the ratio of the square of the radii by inscribing appropriate polygons. He gives this hint. I didn't use it because honestly, I don't really understand why he is making us do this or suggesting that we do this with a proof by contradiction. You don't need to do this with a proof by contradiction. You could do it just by using the limit laws and what we've already established, which is the way that I did it. But I don't know, maybe you could try doing his suggestion, but this seems like a more simple and efficient way of doing it. So this is the way that I proved it. So let Pn and P prime of n be regular n-gons that are inscribed inside circles C and C prime respectively. Then by the limit laws and by part C above, if you take the ratio of the area of circle C over the area of circle C prime, that's equal to the limit as n goes to infinity of the area of Pn. divided by the limit as n goes to infinity, the area of p prime of n. And by the limit laws, that's equal to the limit as n goes to infinity of the ratio of the area of Pn over the area of P prime of n, which is equal to the limit as n goes to infinity of r squared over r prime squared. Since r squared over the r prime squared is a constant, the limit is equal to the constant, so that's equal to r squared over r prime squared, where c has radius r and c prime has radius r prime, and that establishes the fact. Okay, question number 12. Suppose A and B are two non-empty sets of numbers such that x is less than or equal to y for all x in A and all y in B. Part A, prove that sup A, which is the supremum of A, is less than or equal to y for all y in the set B. Okay, so here's the proof. Since every y in B is an upper bound for A, then obviously the supremum of A is less than or equal to y for all y in B, just by the definition of the least upper bound. Okay, and then part B says prove that sup A is less than or equal to inf B, or in other words, the supremum of A is less than or equal to the infimum of B. And again, this is a relatively straightforward proof. From part A, supremum A is a lower bound for B. Therefore, supremum A less than or equal to infimum B by the definition of greatest lower bound. And that's it. Okay, question 13. Is this the last one that I did? I guess it is. Okay, last one for this video. Let A and B be two non-empty sets of numbers which are bounded above, and let A plus B denote the set of all numbers x plus y with x in A and y in B. Prove that supremum A plus B equals supremum A plus supremum B. Again, here he gives a hint. The inequality sup A plus B less than sup A plus sup B is easy, and he asks why. I'll explain when I show you my proof. To prove that sup A plus sup B less than or equal to sup A plus B, it suffices to prove that sup A plus sup B less than or equal to sup A plus B plus epsilon for all epsilon greater than 0. Begin by choosing x in A and y in B with supremum A minus x less than epsilon over 2 and sup B minus y less than epsilon over 2. So I used his hint here for this one. Okay, so by definition, x is less than or equal to sup A and y is less than or equal to sup B for all x in A and y in B. Therefore, x plus y is less than or equal to the supremum of A plus the supremum of B, just from, properties of inequalities for all x plus y in A plus B. That's the answer to the question where he asked y up above. So therefore, sup A plus sup B is an upper bound for A plus B. Okay, that implies that sup A plus B is less than sup A plus sup B. Next, for epsilon greater than 0, we can find an x in A and a y in B such that sup A minus x less than epsilon over 2 and sup B minus y less than epsilon over 2 by definition of supremum. Therefore, sup A minus x plus sup B minus y is less than epsilon over 2 plus epsilon over 2, which is epsilon. Or in other words, sup A plus sup B is less than x plus y plus epsilon, which obviously is less than or equal to sup A plus B plus epsilon by definition of supremum. Then sup A plus sup B minus epsilon is less than sup A plus B, less than or equal to sup A plus sup B for all epsilon greater than 0. That obviously implies that sup A plus sup B is equal to sup A plus B, because the two inequalities, give you equality. Okay, so that's all the problems that I did so far. Like I said, let me just stop the screen share for a second. I actually do want to do some more of the problems from the exercise set in chapter 8. So I'll have to make a second video for this exercise set, which I'll hopefully get around to sometime soon. It's been kind of a hectic month for me. Things keep coming up as they tend to do, So, but I'll hopefully this week I'll be able to post the rest of the exercise set, and then maybe I'll even have time to do the summary for the appendix for chapter 8. So I'll see you guys in the next one. Let me know what you think down below, as always. Sorry for my low energy in this video. It's mainly because it's just so hot in here. I think I should open the window when I make my next video. And also I got my just to remind you, I have my March 1st vlog coming up soon too. Maybe I'll either post that tonight or tomorrow or something. So just keep an eye out for that, and I'll see you guys in the next one.